guys, welcome to our first lesson in Unit 4, Acids, Bases, and Salts. And today we're going to look at the basic definitions of an acid and a base, the basics of acids and bases, how they work, and how to do pH calculations of strong acids and bases. So first we have our definitions of acids and bases. The first definition is called the Arrhenius definition. And the Arrhenius definition is the definition of an acid or a base that you are used to. So in any previous science class, when you talked about acids or bases, they were defined as the following. An acid produces H+, or the hydrogen ion in water. And bases produce hydroxide in water. And so we can see that in each of these examples. So HCl, hydrochloric acid, is creating H3O+, and I have a slide later that explains to you that H3O+ and H+ are the same thing. I'll explain that later. And then we see here that ammonia is creating hydroxide over there. So that's the normal definition. So hydrogen is in an acid, hydroxide is in a base. Another definition of an acid or a base is a Lewis acid or a Lewis base. Now, we're not going to see these very often. We're not going to use them very often. You just need to be aware of the Lewis definition. So if an acid is a Lewis acid, it is an electron pair acceptor. It has an open orbital that can accept an electron pair. A Lewis base is something that can donate an electron pair. And so you can see in these two examples, here the base is donating the electrons to the acid. Again, here base is donating the electrons to the acid, and it forms what's called a Lewis complex. Again, we're not going to see these very often. You just need to be aware of that definition. Finally, and I would say most importantly, is our Bronsted-Lowry definition. So this is the definition of an acid that we're going to kind of take and run with. That's what we're going to be using mostly throughout this whole entire course. And what the Bronsted-Lowry definition of an acid and base does is kind of just broadens out what is considered an acid or a base. So it allows us to see that things that don't typically look like an acid or base to us can actually create acidic or basic solutions. So a Bronsted-Lowry acid is just anything that can donate that hydrogen proton. So a generic reaction would be any acid. So HA just stands for any acid because it's got that hydrogen. And it's going to donate that proton, which leaves A-. So that is what we call, and we'll go over this in a minute, the conjugate base. And it creates that H3O+. That means it's acidic. Bases accept a proton. So this B just stands for any base. And it's going to accept a proton to form BH+, which is just the conjugate. And we'll talk about what these are in just a minute. So it's just that base with an additional hydrogen. And then hydroxide, which is what makes this basic. So a base doesn't have to have hydroxide as part of its formula. It just needs to create hydroxide in the solution, one way or the other. So here's where I promised I would explain why sometimes we see H+, and sometimes we see H3O+, and they're actually the same thing. So if we think about a hydrogen atom, it has one proton, one neutron, and then one electron. Well, the hydrogen ion has lost that electron. So the hydrogen ion is just a proton and a neutron. That's it. And because it is simply a proton and a neutron, it's tiny, has a really positive charge. Neutrons are neutral. And if we think about water, water is extremely polar. And oxygen is very electronegative. What I mean by that is oxygen really likes to pull things towards it. And so what scientists learned is that when H plus or hydrogen ions or the hydrogen proton is produced in solution, it is attracted to that oxygen and it attaches itself to that oxygen and creates hydronium. Oops, that's supposed to be an H. So that's what we see. So water plus, this is the hydrogen proton, is going to make hydronium. So either one is acceptable. H3O plus is just a little more accurate. Using H plus leaves out water. So for example, in regular chemistry, you were probably used to seeing that HCl becomes H plus and Cl minus. But that only happens aqueously. The only way for HCl to dissolve into H plus and Cl minus is to be in water. So the more accurate representation of what's going on here is that HCl with water becomes hydronium and chlorine. So if you were to be asked for the dissolution of hydrochloric acid in water, either one would be acceptable. What you've got to be able to do is when you see either one, you need to know that they're the same. Okay, so we talked about how a Bronsted acid donates a proton, donates H plus. So we want to write an equation that shows how each of these can act like a Bronsted acid with water, meaning it can donate a hydrogen to water. So when this donates a hydrogen to water, it will now be H2O, and water, this water molecule will become H3O plus. It donated a hydrogen. So this time when we donate that hydrogen, we're going to be H3O plus Cl minus. Here, when we donate a hydrogen, if NH3 is neutral, then NH2 is going to have a -1 charge, plus H3O plus. Here, when I donate that hydrogen, I'm going to have H3O plus CH3CO2 minus. Now, if you're a little confused about how I figured out these charges, all you got to think about is adding +1 or taking away +1. So if this had a +1 charge, H3O plus, when it loses that hydrogen, it's now, of course, neutral. If this was neutral and it gains that H plus, it now has a +1 charge. Again, down here, both of these are neutral. Well, when this loses a +1, the remaining thing is negative, and when this gains a +1, it's now positive. So loses a +1, negative, gains that +1, positive. Loses a +1, so it's now negative, gains a +1, it's positive. Also, our charges have to stay balanced. So up here we had a +1 in the reactants, so we got to have +1 in the products. Here we were neutral in the reactants, so together these have to neutral. Again, for the next two, neutral in the reactants, together these keep the products neutral, considering them all together. So you can check your work by making sure you wrote your equation correctly because your charges should balance. So now we're going to switch gears and we are going to write these as how they would act as a Bronsted base. So now instead of donating a hydrogen, they have to be able to accept a hydrogen. So now they are taking the hydrogen. So now we have H3O plus and OH minus, because this gains a hydrogen and this loses that hydrogen. So accepting it becomes H2O and OH minus. Accepting a hydrogen. Now, if this is neutral now, when it gains a positive hydrogen, it now becomes NH4 plus OH minus. Now, if this is negative right now, -1, when it gains that hydrogen, it's now going to be neutral. And again, I'll point out our charge is balanced. Neutral in the reactants, so these combine to be neutral. -1 in the reactants, -1 in the products. Neutral in the reactants, these together become neutral. -1 in the reactants, -1 in the products. So that's how we write the equation for something acting as an acid with water or a base with water. So when something acts as an acid or acts as a base, it creates a conjugate. And so that's what I mentioned in one of those early slides when I called it a conjugate acid and a conjugate base, and I said we would go over that. So a Bronsted acid creates a conjugate base, and a Bronsted base creates a conjugate acid. And we call these two conjugate pairs. So a conjugate base is the remaining product after an acid donates a proton. So if you look right here, here's my acid. Once I got rid of that hydrogen, what was left was A minus. That A minus would be able to then take on another proton to reform the original acid. So a Bronsted acid becomes the proton and the conjugate base. Now a conjugate acid is just the opposite. It's the product made when the base accepts a proton. So now I'm starting with this base, generic base. I'm gaining a hydrogen, and so I become an acid BH+, because now that BH+ would be able to donate a hydrogen and return back to the original base. So these are called conjugate acid-base pairs. So instead of just using generic ones, let's look at actual examples. So this first acid is nitrous acid, HNO2. So it's going to donate a hydrogen, and what's left is NO2 minus, which is the conjugate base, because NO2 minus, if it gains the proton back, will now be the original acid. So those are conjugate acid-base pairs. What you notice in a Bronsted-Lowry acid reaction or base reaction, if one thing is acting as the acid, the other thing is automatically acting as the base. Because see how this accepted the hydrogen and became H3O plus, which is the conjugate acid, because H3O plus can donate a hydrogen. So that's a conjugate acid-base pair. So now this time we have a base, so it's going to accept the hydrogen to form this conjugate acid. So then if it's accepting the hydrogen from water, water is acting as the acid, because then it gets rid of its hydrogen and creates the conjugate base hydroxide. So here is where we see that using a Bronsted-Lowry definition of an acid and base expands what can be considered acidic and basic. Because water is acidic, water is neutral. So by its pH, but in the Bronsted-Lowry definition, if water gives away a proton, it is considered a base. And if water takes in a proton, if water gives away a proton, it's considered an acid. And if water takes a proton, it's considered a base, based on the Bronsted-Lowry definition. So here is also an example where we see something that does not have hydroxide. So normally you would look at that and say, that's not basic. But what we see is that with water, this compound steals away a hydrogen from water. And when it does that, it creates hydroxide. Well, we know that having hydroxide is basic. So this solution would be basic. So for each of these, I'm asking you to identify the conjugate acid-base pairs. If you would like, you could pause, try to do it on your own, and then click play to check your answers. So what I'm going to do is I'm going to use red for acids and blue for bases. So this is my acid, and so its pair is what's left behind, so that's the conjugate base. So then if this is my acid, then this is my base, and what's left behind is its conjugate acid. So there's my pairs. Acid is the thing that accepts the proton. So we see here, or I'm sorry, I said that backwards. An acid is a thing that donates a proton. So we see here that it is water that is donating the proton. So water is the acid, hydroxide is the conjugate base. The cyanide ion is my base, and when it accepts a proton, it becomes HCN, which is the conjugate acid. Sulfuric acid is the one donating the proton, so that is my acid. Its conjugate base is what's left after it donates the proton. So then chlorine is my base because it accepted the proton to form the conjugate acid HCl. So the thing that is donating a proton is my acid. So again, now this time HSO4 minus donated an additional proton to become SO4 2 minus, my conjugate base. And hydroxide accepted that proton, so it's the base, and it formed the conjugate acid water. So we would call these two a pair, and we would call these two a pair. So those are conjugate acid-base pairs. So I like to use the analogy with conjugate acid-base pairs of volleyball. So a conjugate acid-base pair can only differ by one hydrogen proton. It cannot be multiple protons. It can only be one hydrogen proton. So what I mean by that is if my acid is HCN, then if HCN gives up the hydrogen, it's going to be Cn minus. Now if Cn minus takes in a hydrogen, it becomes HCN, and when this one gets rid of it, it's now Cn minus. Now, if this HCN that we've formed hits the volleyball back, now this becomes HCN, and this becomes Cn minus. And they can go back and forth. And that's what makes them a conjugate acid-base pair. What cannot be considered a conjugate acid-base pair would be something like this. So if I had H2SO4 and SO4 2 minus, that's not a conjugate acid-base pair, because if this H2SO4 gives up this hydrogen, then this becomes HSO4 minus, and this becomes HSO4 minus. Those are not pairs. So in order for this to be a conjugate acid-base pair, if my acid is H2SO4, then my conjugate base is HSO4 minus. Because now when that accepts, it becomes the conjugate acid H2SO4, and this becomes HSO4 minus. So now they are conjugate acid-base pairs. Some species, as you may have noticed when we were writing the acids and bases, they showed up in both lists, and that's because they are something called amphiprotic. They can act like a Bronsted acid or a Bronsted base, depending on the circumstance. So if the thing that it is with is more acidic, then it's going to act like a base. If the thing it's with is more basic, it itself will act like an acid. So an example of this is the carbonate ion. And here I just showed both of them with water for ease of an example. So you can see how it's the same compound acting as an acid or a base with the same partner. So here, if HCO3 minus, the carbonate ion, is going to be an acid, it donates a hydrogen to become CO3 2 minus. But it can also act like a base by accepting a hydrogen and becoming H2CO3. And notice when it acts like an acid, it makes hydronium. When it acts like a base, it makes hydroxide. So another example, of course, is water, because we've seen water be both of those things. So here, water is acting as a base because it is accepting the hydrogen. Here, water is acting like an acid because it's donating the hydrogen. So some species are amphiprotic. They can be both. Another example is NH3, ammonia, because it can gain a hydrogen to be NH4+, or it can give up a hydrogen to be NH2-. So it can be a base or an acid. So you may be asked just to say, what is the conjugate acid or the conjugate base of something? All of these listed here are called amphiprotic species, like we just talked about. They can be both. So what I'm going to do first is I'm going to write the conjugate acid of each of them, and then I'm going to go back and write the conjugate base. So if you want to try this on your own, pause, do it on your own sheet of paper, and then resume. So if I'm looking for the conjugate acid, then the thing in my list is acting like a base. Okay? We can think of the conjugate acid as the base plus H+. So OH minus plus H plus gives me water. H2O plus H plus gives me H3O plus. HCO3 minus plus H plus gives me H2CO3. NH3 plus H plus gives me NH4 plus. HSO4 minus plus H plus gives me H2SO4. H2O2 plus H plus gives me H3O2 plus. So again, if it was neutral and I added H plus, it's now positive. If it was negative and I added H plus, it's now neutral. Now, for the conjugate base, if I'm looking for the conjugate base, the thing itself is acting as an acid. So the conjugate base you can think of as the acid minus H plus. So if OH minus is an acid and it gives away its hydrogen, OH minus H becomes O2 minus. H2O minus H becomes OH minus. HCO3 minus H becomes, just CO3, 2 minus. NH3 minus H becomes NH2 minus. HSO4 minus H becomes SO4, 2 minus. H2O2 minus H becomes HO2 minus. So for each of these, because I lost a hydrogen, which is +1, and all of these began as neutral or -1, they all became either -2 or negative. So something we need to talk about now that we kind of know how acids donate a hydrogen and bases accept a hydrogen is something called the auto-ionization of water, or the self-ionization of water. So in any sample of water, water molecules can act as an acid and base, and one will donate a hydrogen and the other one will accept it. And so what happens is two water molecules create hydronium and hydroxide. And this is in an equilibrium. Now, if I wrote the expression K for this equation, I would only have my products because my reactants are pure liquids. So that's my expression, my equilibrium expression, K, for this equation. I could have given you that last unit and asked you to write K, and that's what you would have written. Well, now we're going to give this specific expression Kw, because it's the ion product constant for water specifically. So if you remember in regular chemistry, you learned that Kw equals 1 times 10 to the negative 14. But you didn't really know what the heck K was, and that was okay for the time being. But now we can interpret that with a K of 1 times 10 to the negative 14, this equation is extremely reactant favored. So if we have a sample of water, most of it is still going to be H2O molecules, but there will be some hydroniums and some hydroxides. But if it's neutral water, they will be equal. Okay, so that is where that constant 1 times 10 to the negative 14 comes from. So what exactly does that constant mean beyond the fact that it's very reactant favored? Well, when we set up this K value, we know with neutral water that these two are equal. If one outweighed the other, it would be acidic or basic. So if these equal one another, I can take the square root of 1 times 10 to the negative 14, and that tells me that the concentration of hydronium and the concentration of hydroxide is 1 times 10 to the negative 7. So if I take the negative log, because pH equals the negative log of the hydrogen concentration, which is 1 times 10 to the negative 7, I get 7. So that's why the pH of pure water or neutral water is 7. Now, something that kind of blows your mind is that this is at 25 degrees. We learned all last unit about how K is temperature dependent. So while we don't normally do anything with this fact, K does change with temperature. And so if we notice here, pH of 7, Kw is 1 times 10 to the negative 14. 25 degrees Celsius is kind of an average temperature. It's room temperature. And so that is the value of Kw in the pH of neutral water that we normally use. But if we look, as we decrease the temperature, Kw decreases and the pH of neutral water actually increases. While as temperature goes up, Kw goes up, and so the pH of neutral water actually decreases. So technically, the pH of neutral water changes with temperature change. Now, what does not change is the fact that the amount of hydronium and the amount of hydroxide are equal in neutral water. So neutral water is still neutral. The pH of neutral changes with changing temperature. The only time you would have to take this into consideration is if a problem told you that the temperature was not 25 degrees, and if they did, they would have to tell you what the new Kw value is, and you'll see that in a later example problem. Okay, so we've kind of discussed this already. Concentration of hydronium and concentration of hydroxide are equal if a solution is neutral. So we can compare these to determine if something's basic or acidic. When they're equal, it's neutral. If we have more hydroniums than hydroxides, we're acidic because the pH will be less than 7. And if we have less hydroniums than we have hydroxides, the pH is going to be greater than 7, and so it's going to be basic. So what I have here is like kind of a screenshot of the pH-related equations that are on your reference sheet. So this one is one we're going to use right now. We're going to get to this one later. These we're going to use right now. We'll get to this one later, and we'll get to these later. Okay? So these are kind of the same ones that you had in Honors Chem, and they're ones we're going to be using right now. So I'm going to kind of reiterate, on your equation sheet, you are given that pH equals the negative log of the hydronium concentration, OH is the negative log of the hydroxide concentration, and that pH plus POH is 14, and hydroxide times hydronium equals 1 times 10 to the negative 14, because this is Kw. All right, so what you are not given is the opposites. So if you are given concentration, then you, if you're given pH or POH, in order to calculate concentration, you have to do the opposite of negative log, and the opposite of negative log is raising 10 to the negative. So if you are given pH, you do 10 to the negative pH to get hydronium. If you're given POH, you do 10 to the negative POH to get hydroxide. So you are given these equations, and these are just the opposite. So they're solving for an equation you're given. So essentially, you're given it, you just have to solve for it. Something else to consider, pH is measured directly. So we have indicators, we have litmus paper, we have a pH meter, all these things that measure pH. We do not have a POH meter. Never, ever, ever is POH measured. POH can only be calculated. And what I have here for you is kind of a little diagram that shows how, given any of these values, pH, POH, hydroxide concentration, or hydrogen concentration, you can calculate any of the other ones using the different equations. So just to do a little practice, again, if you want to do this on your own, you can pause and then start it. When I'm trying to determine pH, I'm going to tell you all of these are strong acids and bases. Because we're going to learn that what that means is that they fully dissociate. We're going to learn this later. But I say that to say it's important for a strong acid and a strong base to then realize that whatever concentration you're given for HCl, that's the same concentration of H+, because this is an acid. For a base, for a strong base, that is the concentration of hydroxide. So for a strong acid, that's the concentration of hydrogen. For a strong base, that's the concentration of hydroxide. So that's kind of your first question. Is this an acid or a base? So for A, this is an acid. So if I take the negative log of 0.2, that's going to be a calculation of pH. Because I'm taking the negative log of 0.2. And we typically round to 2 decimal places for pH. All right, so if the pH is 0.7, then the POH is 13.3, because pH plus POH always equals 14. All right, now this time when I take the negative log, it's of the concentration of hydroxide, so it's going to be calculating POH. So then the POH is 1.85, so the pH is 14 minus 1.85, which is 12.215. Yes. All right, so something you can notice, you can realize if you accidentally make a mistake. If you told me that the pH of sodium hydroxide was 1.85, you should be like, oh, wait a minute, that's acidic, and sodium hydroxide is definitely a base. So it kind of clues you in that you made a mistake. So here we have an acid, so as we expect, we have a low pH, whereas here we have a base, so as we expect, we have a high pH. All right, C is an acid, so taking the negative log is giving me the pH, so the negative log of 3. When we have a really high molarity, you're going to see the negative log of this is negative 0.477. It's actually off the pH scale, and I told you yesterday that that is possible. So the POH is equal to 14 minus negative 0.477, and so that is going to be 14. Let me see. Write this down. Negative log of 3. Yeah, negative 0.477. Yeah, so 14.477. I had something, I don't know what I did on my paper. All right, 14.47, so we're going to say 14.48. So then this would be 0.48. So it is possible to go off of that pH scale, and it only happens when we have really, really high concentrations. And by really high, I mean like, over 2. All right. Finally, this is a base. So taking the negative log gives me the pOH. So the negative log of 0.0031 is equal to 2.51. So the pH is equal to 14 minus 2.51, which is 11.49. So again, this is a base. We expected a large. This is an acid, so we expected a small pH. Something else to remember is that because pH is a logarithmic scale, and it's base 10, any increase is going to be tenfold. So a pH of 1 to a pH of 2, we're actually increasing tenfold in our concentrations. All right, so here's an example where we're given a different temperature. And because we're given a different temperature, we have to be given that different kW value. We can't use our standard of 1 times 10 to the negative 14. So it's asking us to calculate the concentration of each and then the pH and pOH. Well, we know that Kw equals H3O plus times OH minus. It's the expression for the autoionization of water, and it's also given on your equation sheet. So now, instead of 1 times 10 to the negative 14, because we're at 40 degrees, I have to use the Kw given to me. Well, since these are equal, then I can just take the square root, and I get 1.7 times 10 to the negative 7. So that's the concentration of both hydronium and hydroxide. So if I take the negative log of 1.7 times 10 to the negative 7, I get that the pH and the pOH, because the concentrations are equal, is 6.77. So the neutral pH at 40 degrees is actually 6.77. The hydronium ion concentration in a sample of rainwater is found to be 1.7 times 10 to the negative 6. How much hydroxide ions are there? Well, we know that Kw at 25 degrees is 1 times 10 to the negative 14, and it equals the concentration of hydronium times hydroxide. So if hydronium is 1.7 times 10 to the negative 6, then the concentration of OH minus is 5.88 times 10 to the negative 9. That's all for today, and I think it's plenty because we're almost at 40 minutes. Have a great day.